So I can tell you right now, today's Codevember sketch it's probably not going to look all that great. So if you tuned in yesterday to our normal ElmLive, I tried out, at least for my first time, using WebGL in Elm. We spent a lot of time learning about that, and we got some cubes up that animated. But we didn't really do anything with the shaders. And the lighting, there was basically no lighting, and we applied different colors to different sides of the cube in the Elm code. So, my plan for today is to, I guess, kind of have like a cube rave thing going on. And I found this nice lighting tutorial. It goes through the basic types, which is ambient light, which is essentially what we had from yesterday, diffuse lighting, which depends on the direction of the light source, and specular lighting, which also depends on the position of the camera relative to the light source. So I want to try to make a shader today that can combine all those things and lets us put in parameters for different light positions and light colors and have those kind of animate around and have a field of cubes as well. And hopefully that'll look cool. If it doesn't, at least I'll have learned something. So let's jump right in. Oh yeah, I have this other example which has a more full-fledged shader. And I found this cool looking tutorial, the GLSL lighting walkthrough, which looks like it goes through in a lot more detail a bunch of steps of building up a fairly sophisticated shader. So I'm going to try to refer to these and go through this step by step and see how we do. So I have my Codevember GitHub repository here. I'm going to make a new folder for, what are we on, day 7? November 7th. And I'm going to start up Atom, and I'm going to start up ElmLive. And where I'm going to start for this project is not a brand new project. I'm going to go to the WebGL package in Elm. And they have some nice examples. Unfortunately, none of them have sophisticated shaders. But I am going to grab this code for the cube example from here, and we'll start from there for today's code. So in day 7, main.elm, I'm going to paste in this example, this cube example. Great, looks like it compiles. Then I'm going to start up the ElmLive server and tell it that we want to show day 7 main.elm. And it compiled, and we should have this on localhost port 8000. And great, there's our cube. So the first thing we discovered yesterday, well, not the first thing. One thing we discovered yesterday was how to change the camera's aspect ratio. So I'm going to go ahead and change the size of the WebGL canvas to 750 by 500. Now you can see the cube, or the viewport's all out of proportion. So to fix that, we go to this perspective for our camera. And the second parameter we learned yesterday is the aspect ratio. So this is going to be 3/2 now. Great. And now our camera's aspect ratio matches the viewport aspect ratio. Hey Shadow Link, welcome to the stream. And, okay, so first thing I want to do is get a bunch more cubes on here. And also, okay, so a quick overview of what we learned yesterday. We have this scene, and in the WebGL package, our scene is defined here. It's a list of renderables. Each renderable, you give it a Vertex Shader, a Fragment Shader, and a Mesh. and some uniforms. The mesh, you don't want the mesh to change very often during your program, and we actually had a problem with that yesterday where my whole computer ground to a halt because I was making new meshes every frame, which have to be transferred to the GPU. So you have meshes, then the Vertex Shader gets the information about the meshes and produces extra information called, what are they called? Varyings that are sent to the Fragment Shader. And then both of these shaders also get the data here, which is called the uniforms. So the Vertex Shader determines where the vertices are going to be rendered, and the Fragment Shader determines what color each pixel is going to be rendered. So I'm not going to go too much into detail of that. You can watch yesterday's episode if you're interested in some of the details of how we learned all that yesterday. So my goal for the moment is to stop these cubes from rotating. So I'm just going to hard code this angle. And now I want to add some more cubes. So I'm just going to render this same thing. And then what we actually want is another. Okay, so I'm going to pull this out and call this record our uniforms. Give it a type alias. And what we did yesterday was we added a transform matrix that we could apply to each of the cubes. And transform. So I'm going to call this x and y, which are going to be the two values that I want to configure my cubes with. This will be at 0, 0, and the second cube will be at 1, 1. And I'm imagining the cubes will sit kind of on a plane that's going to be below the camera, and the camera's kind of looking down on them. So this transform, which we're adding to our uniforms, which is data that's going to be sent to the shaders from Elm, the transform is going to take the x and y, and let's see, how did we do this? I think we took the identity matrix, and then we did translate 3, I think the function was called, and let me look this up again. So these functions for working with matrices are all in the linear algebra package, in this matrix 4 package. So in here, where's our translate 3? There we go. So this takes an x, y, and a z. So this will be our x, y, and our z will be 0. Actually, I might want to hard code this to be a negative value. And here, the rotation, actually we aren't even really going to need this, but for now I'll just comment that out and put the identity matrix in here. And okay, there's two things called identity, so this is the math.matrix4.identity, and so is this one. And alright, so I'm actually going to multiply these by some units, because one unit is going to be too small for us to see. And we still don't see anything. I'm going to try to move the camera. So this make look at is also from the linear algebra package. Oh, hey Quickly, welcome to the stream as well. Let's see, so is the make camera thing in here? Make look at. So this takes the position of the camera is the first parameter. Got it. So I want to move this. Okay, so it seems like the camera is on the XY plane and up in the Z direction. And looking down. Okay, so I'm just going to move it farther back for now. Great. And maybe let's move it in the Y direction a small amount so we can see the side of our cubes. There we go. Actually, I'll come off to the side. So there's our cube. Okay, so here's why we're only seeing one, or both the cubes are appearing in the same place right now, because we added this new data to our uniforms and we're not using it in our shader. All right. And yeah, today I'm just kind of zooming through everything based on what I learned yesterday. So if you're looking for a slower intro to things, today is not going to be the day for it. I want to get things done for Codevember. All right, so shader, Vertex Shader. This gets the attributes which are attached to the meshes that we create. It gets the uniforms, and I'm going to change this here to take the uniforms so we don't have this big record defined. And okay, so the way this works, actually this GLSL thing is a built-in feature that's part of the Elm compiler and has been for many versions of Elm that lets you define WebGL shaders in the language itself, and Elm actually compiles and verifies the type signatures of these shaders, which is pretty crazy. In any case, any field that we add to our uniforms record, we can access in the shader by adding a line for it here. And actually, I'm kind of curious. If I put vec3, which is the wrong type, I think this will compile in a semicolon. Yeah, so if I put the wrong type in the shader, it actually gives me a type error here in the Elm code, which is pretty crazy. Okay, so we can use the matrix 4, which is the correct type. And what we want to do here is multiply it in. So I actually learned yesterday the right place to multiply the transform in, but basically our rotation is nothing now, but the transform needs to happen before we apply the camera in the perspective. Okay, so we still see nothing changing. So let me pull the camera back some more just to make sure. Oh, and there's the other cube. Okay, so it's too far away, so maybe we do only need to multiply these by maybe 2. And I'm going to do a little bit more, so maybe 2.1. And maybe 2.2. And let's pull the camera back in. Nice. And now, what I really want is for the plane to be kind of on the ground and the camera to be looking out from it. So I'm going to change the Y to be like -15. And the X can be 0. And maybe pull this back even further. Okay. So now, let's go ahead and make a bigger list of these. So let's make like let's see if we can do a 10 by 10 list of these. List.map row, and we'll define row, which will take an X to take this and go to list.map box, and our box now, and actually we want to apply the X, and then our box will take an X and a Y and give us back one of these cubes in the right position. So this should give us a grid, and then we need to list.concat this. Nice. so there's our grid. Actually, let's change this to go from like -5 to 5, and the same thing here. Great. So there's our grid. I'm actually going to space these out a little bit more and change these 2.2 to like 2.5. Cool. So there's our grid. Let's move the camera back a little bit more. All right. So let's get to work shading these things. Actually, and before we do that, I want to put this on a black background. So I'm going to do an HTML. Oh yeah, and we learned this yesterday too. These are just HTML attributes. So we can add HTML attributes.style and put a background color as black. There we go. Yeah, it does look a bit like cheese, weird cheese with like green and purple growing in the middle. Okay, so currently what we have is when we make these cubes, we're putting a color into each vertex. And that color is being used by the fragment renderer to color the cube. So what we're going to want to do is not have each face of the cube colored differently, but I'll wait till we have a bit of the lighting set up before we change that. So let's go to our lighting tutorial. So ambient lighting is what we currently have, where we basically just color the pixel a solid color if it's part of the shape. So let's try to do the diffuse lighting. So diffuse lighting takes, it needs to know which direction the surface is facing, called the normal, and it needs to know which direction the light source is. So we're going to have to add a couple things. First of all, what we have to add is the normal direction to all of our vertices. So that's what this data is, and actually this should really be called Vertex Attributes. Hey Proton, welcome to the stream. So I'm going to rename this to be Vertex Attributes. And we want to add to this the normal direction, which is going to be a vector 3. And that means we need to add the normals to all of the faces. So here when we make a face, it takes a color. It takes an A, B, C, and D, which are the 4 corners. And let's see. So technically we could calculate the normal from 3 of these points. Interesting. So in that case, let's take a quick look in probably this vector 3 package. Actually, I'll search this whole module. Is there anything about calculating the normal? How do you do that? Vector calculate normal. It's going to be just like some kind of product. And I don't know the name of the computation. It's perpendicular. How do you calculate this? The normal vector to the plane, blah, blah, blah. It's probably just like the dot product or something, cross product or something simple. Ah, okay. Shadowlink says it's the dot product. Nope. Wrong, because the dot product of 2 vectors is a float. So maybe it's the cross product. Vector. So pay attention in school, kids, so you don't have to look this stuff up when you're older. I'm going to guess that it's the cross product, but I'd like to see some, yeah. Okay, the cross product is a vector that is perpendicular to both. Great. So here for the face, we're getting 3 points. We can assume, actually, from the way we're using this, that the 3 points are all going to be in a single plane, or any 3 of these points will be in a plane. So if we take the cross product of any 2 of any 3, if we take the cross product of any 2 of any 3 of these 4 points, then we should get the normal vector, which is perpendicular to all of these vectors. So then what's going to happen once we do that? We need to return a list of vertex attributes. Here's where we create the vertex attributes, and here is where we want to attach the normal. So that means we need to calculate the normal, which is going to be math.vec3.cross of any 2 of any 3 of these 4 points. So let's use A and B. And we haven't imported this. Let's do that. Import, exposing, and hey, here's a bug in the Elm syntax highlighter. If anyone wants to fix that, there's a good pull request for you. All right, and what happened? Oh, it's not actually called this. Is it vector3? Yeah, looks like it is. Vector3.cross. Okay, so now every vertex should have a correct normal vector. We'll see if it's correct in a couple minutes. So back to our lighting tutorial. Basically, the Vertex Shader is going to get the attributes from the vertices. It needs to pass the normal vector along through what's called the varyings to the Fragment Shader. So let's set that up so that we can pass it through. So this record here with this V color is the varyings. So I'm going to make a type alias for that, and I'm going to stick it up here by our uniforms type alias. Type alias varyings is this, and this also goes here. And now we're going to add to here the normal. And now if I compile this, Elm is helping us out and telling us what we're doing wrong. So basically we have to update our shaders. So the Vertex Shader, we need to add a varying here, a vec3, which is our normal. And then the Fragment Shader, also the same thing. It's going to get a varying, which is a vec3. So the varying in the Vertex Shader is an output, and in the Fragment Shader, the varyings are inputs. All right, so that compiles. So we haven't set it, so we need to add, what they're doing here is just passing it through from the Vertex Shader here to the, interesting. So here are the attributes. This is where we get the, oh, is this why they do it as a type extension record? Vertex Attributes. Is it going to make me define all of those? Okay, no it doesn't. Great. And then this is also the uniforms. Okay. So we have the Vertex Attributes. So I'm realizing now we can't have things in the attributes and in the varyings named the same. So I'm actually going to rename this one to be called something different. I'll call it vNormal, I guess, to follow the convention that was started for us in the example. So now our varyings are called vNormal. And now from the attributes, from the vertex attributes, we're now also getting the normal, which we calculated previously. And then we're just going to set the vNormal to equal the normal. So all the Vertex Shader does is pass it through so the Fragment Shader can get it. Now in the Fragment Shader, here is hopefully the magic. Okay, so we're going to need to add a uniform that specifies the position of the light. And then once we have that, we also, I guess, okay, we're also going to need the fragment position. So we're going to need a couple more things. All right, so I guess let's figure out everything we need. We need the light position, we need the position of the pixel. Then, here's the payoff. We're going to take the normal, then we're going to calculate the direction that the light is coming from, and then based on that, calculate how bright the pixel should be. Okay, so here's what we're working towards, these 4 lines of code. But first we have to thread a bit more data in. So let's add the light position to the uniforms. Uniforms, light pos is going to be a vec3. Then this, let's just hard code it for now. Light pos is going to be a vec3. Okay, so where's our camera at? So I want to put it kind of behind where the grid of cubes is. So that's going to be 0. And let's put it to the side, I guess, 2. So let's go maybe 10 to the left, maybe 20 back, and have it above, maybe slightly lower than the camera, so 15. So there's our light position. Next, we need the fragment position, and I believe that this model is what we called our transform matrix for the cube. So that's positioning the cube. So we're going to take vec3. Okay, so we're going to stick, what does all this mean? We're going to convert the mesh pixel. So this is basically being reused. Okay, so we're going to take the pixel of the mesh of the cube, convert it into a matrix, then transform it by the transformation, and then get the vec3 back out. And that's the position in the world space of this vertex. Okay, so let's do that in our shader. And then the result of this is that we output a new thing, which is going to go out in the varyings. So we're also going to need a vPos, I'll just call it, which is going to be the position of the vertex. And what the GPU does is it interpolates between all the vertexes and then calls the fragment shader for every pixel on the surface, whereas the vertex shader is only called once for each vertex. Alright, so that means vPos is going to equal vec3, basically just this. And we have position 1.0f. Okay, so hopefully that works. And now our vertex shader doesn't like because it doesn't take all the varyings, I'm guessing. Varying vec3, and we get the vPos now. And we also can access the other uniform that we added, which is a vec3, which is the light pos. Okay, so what is not compiling? So it's saying that the varyings, it's inferring, the type annotation says it should have a vpos varying. Oh, yeah, we didn't add the vpos. Didn't I just do that? Fragment shader. Oh, I see. We didn't add it to our Vertex Shader. Okay, so we have to list this. Varying vec3 vpos. Okay, well great. We have a black screen now. So what did we do wrong? I'm going to comment out, well, how do you, I'm assuming / in here. So we've totally messed things up. Let's see if there's anything in the console. Light pos is a syntax error. Where did we define light pos? In the shader. I didn't give it the right type. This is a vec3. And we still have tons of problems. Model, undeclared identifier, floating point suffix unsupported. Okay. So this was from code I copied, which I guess is from a different version of OpenGL. And now we have model is an undeclared identifier. That's here. And this is actually called transform for us. And this was also from code we copied. Okay, good. That wasn't too bad to debug that. Okay, so we've done nothing. Or we've gotten all the data to come through, and we've calculated the fragment positions and the normals, and now finally, for the money code, we can calculate the lighting. So we're going to take the V normal and the light direction, which we need from here. Okay. So what do we got here? We're going to calculate the norm by taking the V normal and normalizing it. Then we're going to take the light position and subtract the vpos. So this is the direction of the light from the pixel. We get the light direction. Then we take the dot product of the normal and the light direction. And this is like, someone was saying in the chat, this is technically the distance between them, but this will be like proportional. Oh yeah, because these are both normal vectors. This will be proportional to the angle. And then the diffuse, so the color, we'll just use V color for now, and the diff. And then, finally, what do we have? We're just going to use that. Okay, here's the final lines. And this is the output in GLSL. And then our ambient is going to be this. So this is a vec3 ambient equals that. And then the result is the ambient plus the diffuse times the object color, which is actually the color. So then the light color, I guess we need to pass that in also as a uniform. Vec3 light color. And then we don't need the F in here, and then we're done. Okay, so we just added light color to the uniforms, so we need to add that in our type alias here. And then here, light color equals a vec3 of just 111. That's fine. Vec3. Okay, so nothing works. But we have a hopefully helpful error message. Well, somewhere. Doesn't tell us the line number or anything. Cannot convert from a medium 4-component vector to a medium 3-component vector. So somewhere we did something wrong. So v normal is a vector 3. That looks fine. The light position and the v pos are both vector 3s. So we should be able to subtract them and normalize them, get a vector 3. And the normal and the light direction are both vector 3s. We can dot product, we get a float. Light color is a vector 4. Diff is a float, so we should be able to multiply, get a vector 3. Vec4, we're converting the color. Oh, and this should actually be the light color. Yeah, not going to worry about that too much. Shade comes from the uniform, that's a float. Then we get, this should be a vector 3. We multiply by vector 3, get a vector 3. Okay, so that one looks fine to me. That means if we comment this out, we should get a different error message. No, we do not. Okay, so let's try commenting this all out and see if we can narrow down what the problem is. Okay, so that works fine. So apparently it is a problem in here. Undeclared identifier results, so we can define it. Then we need undefined ambient. Then I guess we basically have to pull all this back. Oh, there's the problem. Vec3 ambient equals shade times, Vec4, okay. So that was the problem here. We were too early converting that to a vector 4. Okay. Man. All right, so now, well, the colors look different. I'll give it that. So let's try moving the light and see what happens. 20. I don't really see anything changing. 30 or 300. Yeah, okay, that looks different. So something's happening. Okay, so we have this varying angle thing, which is actually called T. And another thing we learned yesterday from this template, I'm going to change this to 1000, and then T is represented in seconds. So let's have this take a float also, which is going to be T, and then we'll calculate the light position based on that. So let's just make this negative T for the X. And render is causing a mismatch. Right. So in the uniforms, we need to also pass T. Okay, I can kind of see the color changing over here on the left if I looked closely. So I think this is actually working. Why don't we do something a little fancier and maybe like have this rotate around in a circle somehow, if we can do that. So what do we have in vector 3? The matrix 4 has the transformation stuff. And can we use that to transform a vector 3? Yes, we can. Cool. So let's make the light position by doing some quick little animation. I'm just going to have it kind of go around in a circle. So we're going to say math.vector3.transform, and actually let's make a vec3 at x0 and y -20 and z15, and we will convert that and have it rotate. Make rotate. Let me check the docs for that. What does this do? In rotation around a particular axis. Okay. We want to rotate around the z-axis, which here is called k. Okay, so we're going to rotate by t radians around math.vector3.k. This is vec3, and this is actually matrix 4 is the package that that's in. Hey, there we go. So we have a rotating light. All right, we're making some progress. All right, so what's next? Next, dare we try it, is diffuse, or no, we just did diffuse. Next is specular lighting. So let's see if we can add this here. So specular lighting depends both on the position of the light and the normal of the surface and the position of the camera. So let's read through this first and see if we can see what we need to add so we can do it all in one go. We're going to need in our uniform the position of the camera. Sounds good. Then we have this as a constant. Then we find the direction of the camera. Then we find the direction of reflection based on the light, okay? Then we do this fancy code, and they show different examples of the different constants. Then we get the specular, and then we just add it into our lighting. Okay, well that sounds easy actually compared to what we just did. So we're going to add the view position, I'm going to call it the camera position, to our uniforms, which is different from this camera because this is the matrix, the view transformation matrix of the camera. Camera pos is going to be a vector 3, which is the position of the camera in world space. Then, what do we do here? So, camera pos, and I'm going to pull this out into a variable, and this is the camera pos. So we'll let that camera pos equals that in here, so we don't mess that up. Now we should have access to it in our Fragment Shader. From the uniforms, it's a vector 3, camera pause, and I'm just going to reorder these also. So the ambient goes here. This is the diffuse lighting, and this is the specular lighting. So let's grab this code. Specular strength, sure, let's use what they suggest. We have to take the F off. Then we'll grab this. So I'm going to call this the camera direction. This is the camera position minus the vertex position, or in this case it's actually the pixel, which could be anywhere on the surface. Light dir we already have calculated, and this is the norm we already have calculated here too. Then we're going to take this. So this is the camera direction. This is the reflector. Specular strength, light color. Okay, and we have all that. And then we just add this in specular. And we messed everything up. Alright, what's going on here? Camera dir is... oh, I spelled it wrong. Easy. POW, no matching overloaded function. Eee, that's problematic. So this is supposed to take this value and raise it to the power of 32. So GLSL POW function. What is it actually called? How? Can you try this? Seems weird, but works. Interesting. We've got to change that to a float. How? Yeah, okay, that worked. Yeah, that does seem weird, but it works. Well, I can't really tell that this is any different than what we had before. Maybe, let's try this. Oh, well, let's take the diffuse lighting off for a moment. Oh, great. That you can see quite clearly. So that kind of spotlight thing is the specular lighting. So what I actually am going to do is increase the strength to 0.8. There we go. And I'm going to increase the power. They had a couple examples on here. I'm going to increase the power to 128, so it's a bit more specular. I don't know if that's the right term. And this would probably make more of a difference if we had different shapes other than cubes. Here's what we can do. We can kind of rotate some of the cubes in different ways. So where do we do that? We would do that when we make our scene. We'd give different uniforms. I will call this, okay, let's say x plus y is going to be our rotation. And then here, we're just going to make rotate a, how do we want to do this? Let's just use this old code, and rather than T, we will use R for this. Not quite sure what this is going to look like, but let's just do it and ask questions later. Ooh, that's kind of cool, actually. Yeah, man, that is not at all what I was going for. I think this is because we apply the rotation after we apply the other transformation matrix, and really we should have applied the rotation first. But in any case, I kind of like this. The change I do want to make, though, is to have the light rotate farther out. So let's make this maybe 30 for the light position, because I'd like it to kind of fly in front of these. Oh, okay, so then if we lower the Z position of the light, is that doing anything? It's hard to tell. That didn't really seem to do much. Alright, well, let's put the diffuse lighting back on. Yeah, there we go. Now we've got something happening. So now we have the light, as far as I can tell, rotating all the way around. We've added the specular lighting, although it didn't really change much. And the other thing I want to do is make these cubes. I don't want every face of every cube a different color. So let's go through here and let's just change these all to be maybe purple. Yeah. There we go. Yeah, so it's been about an hour now, and I think this is about all I have time for. So we have successfully created a Phong shader, which I learned from here is what you call it when you combine all three of these ambient, diffuse, and specular lighting into a single shader. It's a Phong shader. So we've made one. Possibly there's another Elm package that already defines one even. So that was maybe wasted effort in terms of productivity, but I feel like I'm refreshed a bit on my vector math. And we have a relatively cool looking result here. And yeah, so I'm going to leave it here for tonight. All you Americans out there, go out and vote tomorrow. I'll be doing it first thing in the morning before work. And I will see you tomorrow for another Codevember ElmLive. And I'd like to do some more WebGL. We'll see how I feel and if I have a chance to read up on any more interesting stuff or look at examples before tomorrow. Because I don't really want to feel that stuck in doing something tomorrow. So I might do something simpler, but we will get back to doing more WebGL later this month. If not tomorrow, then shortly after that. So thanks for tuning in. And again, if you are making any Codevember sketches of your own, be sure to let me know on Twitter at AVH4. And Shadowlink says to listen to Riot Make America Great Again, that Russian band. I don't know what it is, but I will trust his recommendation. Alright, I will see y'all next time.